Okay, ladies and gentlemen, let's go ahead and practice applying now our different rules, right, with the chain rule built in. So we've seen how in our highlighter activity we can differentiate a power function, right, that includes the chain rule by taking into account the derivative of the base. And so I know my words for the derivative of a power function overall are exponent times the base raised to the one less, and then times the derivative of the base. And this will now handle composite functions, right? That is the chain rule. So I still need to include times the derivative of the base with respect to p is the 2. And that's why our final answer should be 200 to p minus 3 to the 99. So raise your hand if you already had that. So if you guys already have that, awesome work, you guys. Great. All right, overall, what type of function is number 2? Go ahead and share with the class when I call on you. So overall, what type of function is this? We're going to use a couple different derivatives, but overall, what are we working towards? Vivian?
Trig function.
Absolutely, thank you. A trigonometric function. We know the derivative of a trigonometric function is the derivative of the trig function with the angle. So cosine differentiates to opposite of sine with the angle. My angle in this case is t cubed plus 2t, but then times the derivative of the angle. So the derivative of the angle in this case is quantity, 3t squared plus 2. In this way I can see how the chain rule applies to the trigonometric derivative. So it looks to me like I'll go ahead and group the negative out front. I'll probably keep that as a quantity, 3t squared plus 2 close quantity, and then times the sine of angle t cubed plus 2t. Hands in the air if you already had this. If you already had this one, yes! Good job, you guys. Derivative with respect to k of, ooh. All right, guys, so I'm looking for overall what category of derivatives is this. So overall, what words are we going to start out with for this one? Overall, what words are we working towards? Sophia?
Is it a power function?
This is a power function, right? Where this is quantity to the 1/2 exponent, right? The exponent is 1/2 on a radical function. And so what I might do before I differentiate is to rewrite, not differentiate, but just rewrite this as quantity 11k minus 4k to the 5th, all to the 1/2. By doing this, it's easy for me to see and apply my power rule. So now I'll go ahead and do exponent times the base raised to the 1 less. My base was the 11k minus 4k to the 5th. So exponent times the base raised to the 1 less, and then times the derivative of the base. The derivative of my base is quantity 11 minus 20k to the 4th. All right, Brendan. Love it. So we'll go ahead and maybe regroup that in front. Maybe put that on bottom of the radical. So I probably put 11 minus 20k to the 4th all over 2 root 11k minus 4k to the 5th. Yes, are you down?
Yeah.
Are you thinking this is that's kind of the pretty print way to do it? Right? Backwards type. So raise your hand if you had number 3 correct. You got it correct? Way to go, you guys. You guys are killing it. Good job. All right, 2 to go, and I tried to make them similar but very different. So the derivative of the sine of the cosine of theta. Oh, we can see our nested, right? Our nested trig function here, signaling the chain rule. This is going to be the derivative of the overall function. Sine goes to cosine with the angle. My angle is cosine of theta. So cosine of theta. And then times the derivative of the angle. Well, the angle is cosine of theta. The derivative of my angle then would be opposite of sine of theta. And so what I'm doing is making sure we're timesing that. It's not a subtraction, it's just timesing by opposite sine of theta. Go ahead, bless you. And regroup so that doesn't look like a subtraction, my answer. I'd probably put negative sine theta cosine theta. What? Negative sine of theta times the cosine of theta. That's probably what I'd write. Raise your hand if you had that. So you guys get the same thing? Awesome, good job. And we're 1 to go. And so let's go ahead and take a look at the monstrous number 5. overall, I'm looking to see which words I'm going to start out with. Go ahead and quietly tell your partner which words I'm starting out with for this bad boy.
How?
That's not very quiet. Yeah, that's okay. Okay, in case you didn't hear the first time, Sydney and Cody, overall power rule. You guys, let's do it. So I'm going to do a quick rewrite just so we can see and I don't mess this up. So I'll go ahead and do a rewrite. Remember, this is an operator. dd theta is not a quantity on its own. It does not exist without an input. This operates on something. In this case, it operates on the sine of cosine of theta squared, close squared. So we can see overall we've got a power rule, but we have several links in our chain. Overall power, the base of my power is currently a trig function, and the trig function is a composite function itself with its own angle that is another trig function. So let's go ahead and see if we can get our chain rule here with 4 links. Here we go. The derivative of a power function is the exponent times the base raised to the 1 less. My base was the sine of cosine theta squared times the derivative of the base. The base is a chain rule problem. It's a trig function with a composite function, an inner function. So the derivative of sine overall is cosine with the angle. My angle in this trig function is cosine theta squared. Then times the derivative of my angle. The derivative of my angle is the derivative of cosine theta squared. That overall is a trig function. The derivative of cosine is opposite of sine with the angle. And the final link, the derivative of my angle is 2 theta. You get them all? You get all the links? Yeah. Let's go ahead and reboot this bad boy so it looks a little bit prettier. We'll gain a little bit. I've got the 2 theta, I've got the negative, I've got the 2, so we can certainly group those in front, yes? So let's go ahead and see if we can make that look prettier. It looks like negative 4 theta sine theta squared sine cosine theta squared cosine of cosine theta squared. And let's see what we got, everybody. Here's our negative 2 theta, 2. Here's our sine theta squared, our sine of cosine theta squared, and our cosine of cosine theta squared. Do we get them all? Yeah. All right. I'm dying to know in this moment of truth. Who got number 5 right? That's the big bad mother daddy of them all. Number 5. I did. Not quite half. Not quite half. But in baseball, that's a really good average. All right, you guys. So we've had an opportunity to take care of our stamps today. We will have a multi-pronged assignment, and we'll get a chance then to continue our practice with the chain rule. Some big things coming up.
Yeah.
It's that special time again. No, not that time. We did that. It's time for mental derivatives, okay? Mental derivatives. And so now is where you have an opportunity to embarrass yourself. To show how much you know about your derivative shortcut rules in front of your classmates, okay? And so you can get out your symbolic rule sheet if you want. You can get out your words if you want. It doesn't matter to me if you have your cheat sheet out, that's okay. I want to make sure that you know and understand your derivative shortcut rules and have committed them to memory. So this is just another way to help get you to do that, because even no matter how important I say it is to memorize these, there's nothing like a little of that peer pressure demonstration, right? So you got to be able to recite and apply the words and the rules in front of your classmates. But in order to do that, you guys, in order to do that, we need our classroom numbers. And so we'll go ahead and number around the room, and so we'll use our classroom numbers now. So even though we change seats at quarter, remember, don't forget your classroom number, because we'll use it all semester. And so we'll go ahead and start with Tyler. Obviously, your number 1, 2, 3,
4, 5, 6, 7, 8, 9, 10.
11. No. 11. 12, Kobe. 12, Kobe. Brendan, 11. Everybody got their number? Write it down. Let's get ready. Okay, get ready. Here we go. All right. So we are 1 through 12. I know that you are bubbling with anticipation. I'm going to do probability random. 1 through 12. I believe in you, Sid. Stay strong. Ready? Everybody think. Don't say it out loud. I'm going to call on you with the random number generator. Number 6.
33x to the 10th.
Survey says you are correct. Very nice. Very nice. Good job. 33x to the 10th. Round 2. The derivative with respect to x of 7 sine x. Get ready. Number 3.
7 cosine of x.
Survey says you are correct. Nice job. Keep track. Oh, did you do plus 10? I'm sorry. Plus 10. Plus 10.
Oh.
Derivative with respect to m of 5 cosine m. Get ready. Number 1.
Opposite 5 sine m.
Opposite 5 sine m it is. Plus 10. Keep track of your score. Derivative with respect to x of e cubed. Get ready. Number 11.
E cubed.
Differentiates to?
0.
Yes! Survey says 0. Good job, Brendan. Thank you. The derivative with respect to x of sine of x minus cosine of x. So what is sine of x minus cosine of x? Watch your signs. Unintentional, but I meant to do that. Number 6.
Cosine of x plus sine of x.
You're correct. Good job. Nice job with signs. Positive versus negative. Ooh. Derivative of cosine of x plus sine of x. This thing loves you. Number 7.
Negative sine of x plus cosine.
You're correct. Good job. Good job. Good job. Number 9.
Negative cosine x minus sine x.
You're correct. Nice job. NBD. Derivative of negative cosine of x minus sine of x. Yeah. Number 2.
Sine of x minus cosine of x.
Yes, nicely done. You guys are killing it. All right. So oh, we made it. Oh gosh, I think it's all done. Next time. Grace got called on. Just so you know, Grace got called on like 5 times. And there are only like 11 of those. Okay, here we go. So a reminder that on Monday, the 10th, you're going to have your derivatives rules quiz, right? And this should be an easy way for you to earn points. Remember, we have 2 categories. It's not total points this year. We've got our 85% test quizzes and then our 50% for regular classwork, homework, Bellwork, activity stamps, and stuff like that. And so this is a great way to mitigate a test score like Unit 1. If you weren't happy with that test score, you can certainly raise that by doing well on the derivatives rules quiz. 2 parts. It's symbolic. That's the symbolic rules sheet that you guys picked up after the Unit 1 test. And then verbal. That's what you completed in words last class. Okay, so there's 2 parts. You guys will have 15 minutes to complete it, and it's not meant, right? It's not meant to be a difficult thing. It's meant to be a good thing, but I care that you memorize these rules and you commit them, all right, to memory so that you know them by heart. And you can call them up and use them and apply them. Which, speaking of, we're going to be doing today. So finally, we'll be using derivatives to do some stuff today. You will need your graphing calculators, and I have opened up the emulator because we're going to work with some tangent line type problems and instantaneous rate of change. And so we will be using derivatives to do stuff today, which is nice. We'll continue practicing, and then rules quiz next class. So that's where we're headed. All right. First, though, oh, no, we're good with the stamps. Okay, so let's go ahead and take a look at a couple different applications involving tangent line problems. So what we're going to do is remind ourselves about how the first derivative relates to the instantaneous rate of change, that is the slope, graphically, of a function anywhere along it, and then relate that now to some tangent line type problems, including but not limited tangent lines. We're also reminding you about normal lines. Remember, normal lines are just perpendicular to the curve. Perpendicular to the curve is a normal line. All right, let's find an equation of the tangent line to the curve at the given x value. And so our general scheme to find the equation of a tangent line, you know from last year, right? We need the same three things. We need our x value of the point of tangency, our y value of the point of tangency, and the slope of the tangent line. We're almost always given the x value of the point of tangency. And so we need our x sub 1, that's our x coordinate of the point of tangency. We need our y sub 1, that's our y coordinate of the point of tangency, and we need our slope of the tangent line. All right, so we're given our x sub 1, we can fill that in already. We know that we're interested at the slope of the curve when x equals 1. Where would we go to get y sub 1, the y coordinate of the point of tangency? Riley? Absolutely, so no derivative calculation required. I'll simply plug in 1 and evaluate my function rule. So the square root of 1 over 1 plus 1 squared is 1 over 2. Is that 1/2? I guess getting 1/2.
Yeah.
That's not bad. All right, now the calculus part. So where would I go to get the slope of the tangent line? Right, where would I go to get the slope of the tangent line? Danny?
Find the derivative.
Good. So given y, we'll go ahead and calculate y prime, and then evaluate it at my x value of concern to generate the slope. So let's generate y prime. Oh gosh, I've got a variable function on top and a variable function on bottom. Overall, what type of words? Go ahead and quietly tell your partner, and then share with the class what I'm telling you. Variable expression on top and bottom. So overall, Riley and Vivian? Quotient rule, absolutely. I've got variable expression on top, variable expression on bottom, we're going quotient. Here we go. The derivative of a quotient of functions is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Whoa. Well, no one said it was going to be pretty. Let's go ahead and see if we can't clean this up a bit. What if we work towards simplifying this compound expression? I've got multiple fractions within a fraction. Let's create a common denominator on top. If I survey the top terms, the current denominators are 1 and 2 root x. So I'm going to go ahead and purposely multiply this second term by 2 root x over 2 root x, right? And that way I could generate a common denominator on top. When we do that, I get 1 plus x squared over 2 root x minus, and then here I get 2 times 2 is 4. Root x times root x is x, times the x is x squared. So I get 4x squared over the common denominator that we constructed, all over 1 plus x squared squared. Oh my gosh, we're close. What's the point of that? Well, now I could combine that sum or difference of individual fractions on top as a single fraction with the common denominator that I constructed. So I'm getting 1 plus x squared minus 4x squared. That's 1 minus 3x squared all over 2 root x. And that in turn is all over 1 plus x squared. Now, the reason I'm going all the way here is because I want to practice with our derivative calculation and subsequent simplification. However, we know we just need this derivative for one and only one thing. We need this for the slope of the tangent line. But this is good practice to deal with complex fractions, for sure. So what will I do? Well, I know that dividing with fractions is the same as multiplying by their reciprocal. So I'll go ahead and simplify this by multiplying this top fraction by 1 over 1 plus x squared quantity squared and write a single fraction. I get 1 minus 3x squared all over 2 root x quantity 1 plus x squared close quantity squared. Also that we can do what? Also that we can take x equals 1, right? And figure out our slope of the tangent line. So let's go ahead and do that. My slope of the tangent line will be given by what? 1 minus 3 all over 2 root 1 is 2 times 1 plus 1 is 2 squared is 4 times 2 is 8. So I'm getting 1 minus 3 is negative 2 over 8. this is supposed to be squared, right? And I wrote 4. How's that? 4 times 2 is 8. So negative 2 over 8, which is, oh, we gotta draw negative 1/4. I guess getting negative 1/4. How much easier would that have been to plug in the 1 back here? Not so much in the red. Maybe the black. Maybe the blue. Green. I don't feel bad. I don't have regrets, right? We can't go thinking about going all the way to that green expression. It was easier to evaluate that than any of the previous ones, in my opinion. All right, so who cares? Well, we're trying to generate the equation of the tangent line, and we're going to check graphically, right, with our graphing calculator. So let's go ahead and see what this would look like graphically. I'm going to add a page here. I'm all the way to y minus y squared 1 is equal to n times quantity x minus x. All we need now is to plug in our x value concern, our y value concern, and our slope of the tangent line, so that we can then compare with the original. So here we go. We had y minus 1/2 is equal to negative 1/4 times quantity x minus, what was it? 1. Hey! We could leave it like this if the question, all right, on the AP exam simply asks for the equation of the tangent line. We could stop right here in black, but we're going to enter into our y equals menu, so in the very least we need to add the 1/2 over. We could distribute this if we wanted to, so that we can do draw tangent and see if it gives us the same equation after our visual inspection. I'll go ahead and do it all the way. So I'll do negative 1/4 times x is negative 1/4 x plus 1/4 plus 1/2. I'm going to do plus 3/4. Are you getting that?
Yes.
All right, let's go ahead and verify this graphically now by taking a look on the graphers. Everybody get your graphers, please. So we'll get our graphers. I'll get mine. So we're not having the calculator do it. We're going to enter ours, right? We're going to enter ours, and then we'll have the calculator do it a second, so we have more tools in our bag and we can practice because we had a long summer, right? So we'll go ahead and enter our original. Our original function was, got a whole lot going on here, Mr. Fritz. Our original function was the square root of x over quantity 1 plus x squared. And we're looking at x equals 1. If I do a window that's smaller here around 1, maybe like negative 1, 2, 3, and negative 1, 2, 3. I'm going to try negative 1 to 3 and negative 1 to 3. If I don't like it, then we'll change it. So here's there's our function. And there's our window. Okay, great. So what do we want to do? We want to enter our generated, right, our algebraically generated tangent line equation and see if it touches the curve at x equals 1. Would be our old school way of doing this. So I'm going to go ahead and enter in a different y equals menu. Y equals negative 1/4 x plus 3/4. Yes? That's the way I feel in this class. Plus. Extra good. Extra positive, Riley. Extra positive. Thank you. My bad. And we'll check it. Oh, gosh. Doesn't it look like it comes and just touches the curve? Now, we're used to tangent lines not cutting through a curve the way the secant lines do, right? We're used to tangent lines coming and just touching the curve at a given point. However, we're also used to functions that have a nice concave appearance, right? Where we can kind of think of balancing the ruler on the outside of a basketball. The tangent to a basketball wouldn't cut through it. Here, we cut through the curve. Well, that's also because the concavity of my function changes. And so what we care about is that the instantaneous rate of change, that is the slope at my point of tangency, of the curve is exactly the same as the slope of the tangent line. And so we could do that graphically a couple different ways using our calculator and the built-in capabilities. One way, recall, would be to do second traces calculate. If we calculated dy dx, right? That's the sixth option. at the x value concern 1, enter, the cursor would jump on and spit out the instantaneous rate of change. It should be the same as our calculated slope of the tangent line that we did algebraically, is it? Well, it's doing its darndest, right? It's telling me negative 0.2499998. So we had to recognize that that's trying to tell us negative 1/4. Yes? Second way, we could draw a tangent line using the built-in capabilities of my calculator and have it spit out an approximation for its equation. So another way to check using your built-in capabilities of a grapher would be to do what? Second program. Everybody, second program. Which option would we want here? That fifth option is tangent. And then I tell the calculator with the x value concern, I want x equals 1. Enter. And how sweet is that? It's tracing over my previously entered equation and spitting out an approximation for it. Did we mess up? No, it's doing its darndest to tell negative 1/4 x plus 3/4. So are you guys starting? Oh boy. Are you guys starting to remember? Yes, from last year? Yes?
Yes.
Awesome. Let's do some more. That was pretty cool. Another question that's typically asked is at what values of x, if any, does the curve have horizontal tangents? So what values of x does the curve have horizontal tangents? So this is different. Instead of giving us an x value of concern and asking us to do something with it, it's asking us to determine, right, what x values satisfy some constraint. So this, why would we care about horizontal tangents anyhow? Right, why would we care about horizontal tangents in the first place? And I'm not saying you would go there. Why would we care about horizontal tangents in the first place? No, we don't care about horizontal tangents? We do, totally, because that's what feature of a graph. Yeah, typically, not always, but typically, right? That's where we're seeing a maximum or a minimum in a function. And realistically, right, that's what we care about when we're trying to do our application problems. We want to know when the maximum profit occurs, or when the minimum gas mileage or consumption occurs. Right? We care about that maximum minimum stuff. Must have been something I said. Let's go ahead and do it. So what are we going to do? Well, we want to know about horizontal tangents. That means we want slope of 0. So what quantity gives me slope? Well, not y, but y prime. Go ahead and tell the class y prime when I call on you. So what would our y prime be? I know you're ready. Brendan?
It'd be 3x, no, 4x3.
Yes.
Minus 6x.
Awesome. That's what I'm talking about. Good job. Good job. And we want this, right, slope, because y prime represents the slope of y anywhere along it, to equal 0. So that's our key here. A horizontal tangent has a slope of 0. And so it's as easy as setting up this equation, solving for x. That'll generate the x values. Now we're going to verify graphs. So we're just trying to use today to remind you about how derivatives, right, can answer questions about instantaneous rate of change and slope problems. So what are we going to do? I'm thinking factor first or fail. So I can go ahead and factor out a 2 and an x. That will leave me with 2x squared. Is that right?
Yeah.
Minus 3, is that right? Yes? Equals 0. Now I can set each individual factor equal to 0 and solve. So setting the first factor equal to 0 and solving, I get 2x equals 0, so x equals 0 is one place. Setting the second factor equal to 0 and solving, I get 2x squared minus 3 equals 0. 2x squared equals 3. X squared equals 3 halves. So this is 2 values, isn't it? Isn't this 2 values? They do it, right? Add over 3, divide by 2, take the positive and negative square root. So the positive and negative square root of 3 halves. Then we can certainly rationalize the denominator there. and get and get what? Root 6 over 2. But I'm going to leave it like this because this is easier to work with. So I'm not going to rationalize the denominator. I'm going to leave it like this. Okay, so we're predicting my curve to have horizontal tangents at x equals 0, at x equals positive root 3 over 2, and at x equals negative root 3 over 2. How could we verify that? How could we verify that with our calculator? Any idea? I think of at least 3 ways, right? What's one thing we could do? Kobe?
Graph it and then do calc.
I'm down. Let's do graph it, calc 0. So everybody, let's go to the graphers. I like Kobe's idea. To the graphers, and we're going to go ahead and clear out that open. And I'll zoom 6 it because I don't know where we're going to be. And then I'll enter my original function. So my original function was x to the 4th minus 3x squared. Oh, pretty print. Oh boy, can't live with it, can't live without it. So x to the 4th, get out of there. Minus 3x squared. Yeah.
Should we enter the derivative?
Great question. So do we want to, oh, you were saying see if it crosses 0.
Yeah.
I was saying second calculate dy dx 0, and you're saying enter the derivative. Good, good. So I like that idea too. It's the same thing. Unless we made a mistake in our derivative calculation, right, then we could be verifying that our incorrect derivative had zeros at the x value we found and not expose any mistakes. So I want to go back all the way to the original, but yes, that would certainly work, so long as our derivative equation is correct. Good. I'm doing second calculate dy dx and seeing if it equals 0, and that's what I thought you meant first. But yes, your way would certainly work. Do you guys see what Kobe said? He said do the derivative equation and see where it equals 0 by second calculate 0, and then left bound, right bound, guess, and when it jumped on the x-axis, right, that should say x equals 0 or x equals root 3 over 2. Good. All right, so did I figure out how to do my pretty print exponents yet? Is that right?
Mm-hmm.
Graph? Don't know where this is. All right, I'm going to modify my window a little bit so I can get in there. So I did my zoom 6, and I'm going to change that because I want to be able to see right in around positive root 3 over 2 and negative root 3 over 2. So I'm going to go ahead and zoom in a little bit differently. I'm going to window, and it looks like negative 3 to 3 and negative 4 to 4 might be a good starting point. So I'm going to do negative 3 to 3 and negative 4 to 4. And if I don't like that, then I'll just change it. How do we do? Pretty good. And next up, we're going to do, right, we're going to do 2 things. First, we can do second calculate, and I want dy dx, the instantaneous rate of change of y with respect to x, so that's 6. Oh. So I want that, and I'm going to do 3 places. Ready? I'm going to do 0, enter. Its predicted dy dx value is 0. Now I have to be careful with that because it uses symmetric difference quotient to do that. So if this were like an absolute value graph, it would still predict 0 at the corner or kink or cusp, even though the first derivative does not exist at a corner, kink, or cusp because it's a rapid change of direction and the left-hand slope doesn't match right-hand slope. However, we know this is a polynomial, so it's smooth and well-behaved. What are we going to do for the other ones? We'll simply enter our x value of concern. We want x equals second root 3/2. How's that? Yes? Hey! That's bad news. Right? That's bad news. It's okay, I didn't do second calculate dy dx again. I just did x equals and it just evaluated my function value. So I have to do it every time, it looks like. I thought I didn't have to. So I'm going to calculate dy dx again. Then I'm going to do root 3 over 2. And enter. Come on, come on. Dang it! 4.8. We were way off. Wait a minute, rascally rabbit. It's 4.899 times 10 to the negative 6. And so 0.000050 zeros 498. So again, our calculator is imperfect. It's giving a decimal approximation, but this is trying to say 0. So we're okay. And one more I want to check. I'm going to do it still one more time because I still think it will. Yeah, So if you just don't press X again, just press the X value of concern. So I do negative second root 3 over 2. I'm like, last question one. Negative root 3 over 2. Let's try it. No. Gotta do it. Second calc 6. And just negative root 3 over 2. Third time's the charm. Hey, there we go. All right. So what's another way we can do this? That was one way. That was the second way. First derivative and do the zeros. But if we made a mistake in our first derivative calculation function, what's another way we could do it? Grace?
You could graph the derivative and then graph a line horizontal line at 0.
So graph the derivative, graph the horizontal line at.
Graph y equals 0. And do like the intersection.
Oh, yes! Second, calculate intersect of the derivative equation and the horizontal line y equals 0 to see when. Second, calculate intersect. I like it. Left bound, right bound, guess, and then intersect. Excellent. I was thinking of drawing, right? I was thinking of drawing a tangent line at x equals root 3 over 2 and see if it's flat. See if it's horizontal, right? So I want to try that. Second draw, tangent, and I'm going to do at, well, what the heck? We'll do negative root 3 over 2. And we'll see if it's horizontal. And then it looks horizontal. And then it looks horizontal. That's pretty sweet. Awesome. Way to go. What questions do you guys have about our horizontal tangent question? All right. Well then, let's go ahead and try another. So consider what values of x, if any, does the curve have a horizontal tangent, and then find them. We're going to restrict our domain, in this case, to 0 to 2 pi. So let's suppose we're looking at x plus sine of x. We're only going to look on 0 to 2 pi. All right, so we want to know again when our slope y prime equals 0, what's our y prime function going to be this time? What's y prime going to be this time? Courtney?
1 plus cosine of x.
1 plus cosine of x. Thank you. And we want to know when this equals 0. So we'll go ahead and set equal to 0 and solve. I'm getting cosine of x equals negative 1. Does that happen on 0 to 2 pi? Does cosine of x equals negative 1 on 0 to 2 pi? I hope so. Where, Marissa? Thank goodness for your quiz. That's so right. So it looks like cosine of x equals negative 1 at x equals pi. Anywhere else? Anywhere else on 0 to 2 pi? No, not on that restricted domain. Good. All right, let's go ahead and do a quick check. Can I check? Yo. Yow. What's our original? X plus sine x, thank you. X plus sine x, close. And what would be a good window? We were going from 0 to 2 pi, so what I'm going to do is negative pi over 4 to be just a little bit to the left of it. And then 2 pi would be 8 pi over 4, so I'm going to go to 9 pi over 4. Now, I'm just picking values a little bit to the left of 0 and a little bit to the right of 2 pi, just so that I can see kind of my window of x values nicely. And I don't know what that is. A decimal looks like it's about 7.06. My y min and max on 0 to 2 pi is going to go all the way to 6, so I'm not sure. I'm going to try negative 4 to 3, 6. We'll see. I don't know if that's good or not. If it's not, we'll just change it. So there's that. Aww. Very nice. So what do we say at pi? Second. Calc. 6. Pi. Can we do pi? What do we do? 1.667 times 10 to the negative 7th. This one's even better. Approximation. Trying to tell us 0. That's pretty sweet. What else can we do? Second draw. Tangent. 5. Ooh. I'm going to enter pi again. Ah? That's pretty sweet. That's pretty sweet. Cool. Alright. And when we go, at what points on the hyperbola x times y equals 12 is the tangent line parallel to 3x plus y equals 3. So we're trying to look at another layer now. First we've seen how can we calculate, right, the slope or an equation of a tangent line at a particular x value. Our next layer was, well, let's find some x values that satisfy a given constraint. And now let's go ahead and say, well, and that constraint was equal to 0. Now let's say, let's find some points in their entirety, right, that have a tangent that is parallel. So we're building in complexity here. So who's got a scheme of attack? What do we want to do here to attack this problem? Go ahead and quietly tell your partner to come up with a plan. And then share your plan with the whole class when I call on you. So what would be a good plan for this one?
Well, I got Those are the winners. Oh, that's not one. But no, that was well, yeah. Why you just want to
So we got a strategy. Do we have a strategy, a plan of attack that we can share with the whole class?
Yeah.
Yeah? Who wants to share their strategy?
Cool, yes.
Tyler and Emily?
So you find the slopes of each of them and set them equal to each other.
Find the slopes of each of them and set them equal to each other? Vivian, Riley, what were you guys saying? So yeah, all right, we want the slopes to be the same because that's what determines parallel, right? Parallel is that their slopes are the same, absolutely. So we get the slope of the first, we can determine the slope of the second, whether or not that includes the derivative calculation or not, because it looks like a linear function, and set them equal to each other and then solve for x. Absolutely, great plan of attack, you guys. Those are both correct. And so let's go ahead and first rewrite my original parabola. Hyperbola. That was a gross exaggeration of a function. We're going to go ahead and solve that for y equals what? 12 over x? Is that right? And I don't know that we have to differentiate this. We certainly need its slope, but if I recognize this as a linear function, then whether I differentiate or not, I can recognize that line has a slope of what? So I'm going to take y equals 12 over x and set equal to negative 3? No, the plan was first derivative set equal to 3. So let's do that. So here we go, y double prime. This is the power rule problem. 12x to the negative 1 is the current exponent, so negative 12x to the negative 2, so I'm getting negative 12 over x squared. Oh, prime.
Good catch.
Thanks. Is that a correct single prime calculation? Yeah. Set equal to negative 3. I think this is going to work. I feel good about our plan of attack. So negative 12 equals positive 3x squared. X squared equals 4. Yes? X equals plus or minus 2. Can we do it? All right, guys. Or multiply both sides by negative 1. Or divide both sides by negative 3. However you guys want to do it. All right, I'm dying to see if we're right, and hopefully we can have some practice. And so what I'm going to do is go ahead and enter my original hyperbola. Remember that has to be solved for x. And, oh, we didn't find the points. We didn't find the points. We just found the x values. Right? We still need to find the y coordinates in order to list the points. So I got to pay attention to detail here, Mr. Fritz. We wanted to find out what points. And so the points then would be 2 comma and negative 2 comma. Don't know. Where would I go? Well, right here. So I get 2 comma 6. Is that right? And I get negative 2 comma negative 6. Hey, well, this is at least giving me a good idea for a window. So I'll do that, and I'll do window -4 to 4. No, -5 to 5. I'll try. And -8 to 8. I don't know if that's good or not. No, I want to make it bigger. So I'm going to go -12 to 12. No, -10 to 10. It's perfect. No, quit trying to give me a change. I'm constant. -10 to 10. I just want a nice picture. Yeah.
Wait, what are we entering, like the Y1, Y2? Both of those?
Nope.
Just that?
Just that.
Okay.
Well, yes, both of them. Both of them.
Wait, so 12 over x is Y1 and then Y2 is -3x plus 3.
Yep.
Okay,
That's what I'm gonna do.
perfect.
So Sydney wants to. I wasn't gonna do that, but Sydney wants to enter both of these. So I'm just kidding. No, let's do it. Let's do it. Let's do it. So why are we entering both of these? Because we want to see where is my curve in blue parallel to the red line. So we've got lots of options here, right? We could draw at those x values and then see if its tangent line looks parallel, and then see what its slope equation spits out. And it should be the same as the slope of that line. Yes, let's try it. So I'm going to second draw 5 tangent 2, enter. Come on. Does that look parallel? Yes? While we're still here, guys, let's do second draw 5, -2, enter. Come on, make money. And let's see what it says. -3.000000075x. Yep, so it's trying. That's pretty sweet. I'll keep that for $1. Awesome. What question do you guys have about a quick and dirty tangent line refresher? I tried to reframe the questions about tangents a little bit differently, but still, right, same stuff. First derivative gives us a slope anywhere along the curve, and the slope of the tangent to the curve at a particular value is my y prime function evaluated at my x value concern. You guys good? Awesome. So what's going on today? Today we're going to have an opportunity to practice your chain rule. Then you're going to have bookwork problems on OTL that I included as part of your slide. You guys get the last one? Did I get the on the printout this time? Just fit, right? Okay. So what's up? Well, when you work on your chain rule practice, you're going to take your smartphone, your electronic device, you're going to check with the keys. When you agree, you're going to come up to the front desk, and I'm going to issue a stamp at 8 and at 16, or only after you've checked them and they're all correct. Then you can work quietly on your book assignment, and you can do that with a partner so that we practice and make sure that you guys are good to go. Don't forget, quiz next class, and I'll go ahead and stop the recording.